So now let's practice integrating in spherical coordinates. So if you remember, we had to convert dA when it was in rectangular to r d theta for polar and cylindrical coordinates, right? So it became r d theta. So we also need to have different forms of dv for rectangular and spherical coordinates. So dv, remember, is dx, dy, dz, and of course the order is not really relevant. And actually, let me just review cylindrical in here. Cylindrical coordinates had dv equal to r, then dr d theta dz, or dz dr d theta is the more common way to write it. Okay, so how is that going to work for us? For spherical, it's going to become rho squared sine phi, and then d rho d phi d theta. All right, and if you want to see it proved, it's in your textbook. You can look it up on Canvas. It's not a big deal. I'm not going to get into it. Okay, so then that means that we want a triple integral. Our triple integrals over the solid D will be of f of rho phi theta, and then it'll be rho squared sine phi d rho d phi d theta. All right, let's do one. So we're going to use a triple integral to find the volume bounded by the xy plane and above, or bounded below by the xy plane and above by the object x squared plus y squared plus z squared, which we all know hopefully is a sphere, right? That's a sphere, which is a classic example of when spherical coordinates are really helpful, is when you're working with a sphere, right? Okay, so let's look at this. All right, here it is in Maple. So I just plotted in spherical coordinates, and I plotted 6 because that's what rho squared is, right? Rho squared is 36, so rho is 6. So it's a sphere, right? But we don't really want the whole sphere. We want the sphere part that's bounded on the bottom by the xy plane. And I know this doesn't look like a sphere, but it is. It's because the scaling is not constrained here. So that's why it doesn't look like a sphere, but it is. Okay, so let's draw that. So we really don't need the whole sphere. We need the top half of the sphere. So top half of the sphere comes like that, and then it's going to go around like this. There we go. All right, so pretend that's a sphere. Right, I know it looks like a dome. Okay, so there's our sphere. Now, we want to set up our volume. Now, volume is the triple integral over the solid of 1 dv. Okay, so that will be the triple integral of 1, and then we're going to have to write this rho squared sine phi, and then I'm going to do this in different colors. D rho d phi d theta. All right, no problem. We can do this. Okay, so the easiest parts to figure out are actually rho and theta in this case. So if you imagine a spoke coming out from the origin and poking out that sphere, this is a sphere that is rho squared equals 36, so rho equals 6. And that's exactly where we're hitting, right? So we're going to go from rho is going to go from 0 to 6. Theta. Well, it's the whole sphere, right? It's well, the whole top half of the sphere. So theta, if this is the positive x-axis, theta starts here and goes all the way around and does a full rotation, right? Because this is the x-axis and this is the y-axis. And so this is no problem. That's going to be going all around. That's 0 and 2 pi, right? They didn't say just look at the first octant or something like that. All right, now what about that phi? Well, in this case, it's really easy to figure out because phi goes from the positive z-axis down until it stops where this object stops, which it's going all the way from here all the way down to here, and then it gets rotated around. So phi is pi over 2, right? And theta is 2 pi, right? So phi starts at 0, top, and then it kind of chugs down until it gets to the bottom, right? And then you spin it around with the theta. So phi is going from 0 to pi over 2. Hey, everything's constants. Woohoo! Now, you'll notice everything's constants. However, there's a rho squared and a phi in here, which means you cannot use your trick for rho nor for phi because there's values in here. However, I see that there's no theta anywhere in any of this. So I can use my trick and go, hey, cross off this, cross off this. We have 2 pi out in front. Then we have an integral. Now, we have to be, we could actually do this either way. It's kind of which way would you like to integrate first? Would you rather integrate sine to get negative cosine, so do the phi first, or the rho first? Because since everything's numbers over here, it doesn't actually matter what order we go in. But rho is just as easy, so I'll leave it as in the order that it's in. So we're going to go 0 pi over 2, and then I'm going to integrate rho squared. So I'm just going to leave sine phi just sitting there. And then it's rho cubed times a third. Now, we could leave the third there, or we can bring the third out in front, right? And then we're taking that from 0 to 6. So actually, I think I'm going to bring this out in front, and for starters. And for another starter, 6 cubed, right? We can find what that is. That's 216. So we can just kind of bring everything out in front, right? If we want to, and say, look, this is 2 pi over 3 times 6 cubed, which is 216, because everything's a constant. And then we're still integrating sine of phi. Oops, I forgot my d phi. There we go. From 0 to pi over 2 d phi. So 6 and 0 is 216, right? So I just kind of pulled all that out in front, just to make it my life easier. Okay, so then I'm going to integrate sine of phi, which is negative cosine of phi. And this, by the way, turns out to be 144 pi. All right, so 144, and then this is negative cosine of phi from 0 to pi over 2. Okay, so that's 144 pi. And then negative cosine of pi over 2 minus negative cosine of 0. All right, so let's think about that for a second. Minus a minus is really plus, so we can kind of crisscross that and make that into a plus sign. And then negative cosine, the cosine of pi over 2 is 0. Right? This is 0. So it's, and this is 1. So it's really 1 times 144 pi, which would be 144 pi. Oh, rats. I didn't give a unit. All right, so let's assume x, y, z in meters up here. So if we find the volume, then this would be meters cubed down here as our unit. And just so you can see, I checked the integral. I actually used rho and phi from the Greek palette down here. You can use them. They're great. They're in there. And then it'll tell you all of them. And then there's the numeric value as well. This is the original integral as set up, and this is my last integral, so I can prove to myself that I did it correctly, which I did.